Bets on proportions. This is the same setup as a bet on the average, except instead of the t-value, a proportion always uses a z-value, a standard normal value. And it's purely because the proportion is actually from the binomial distribution rather than a normal distribution. All the rules apply except that it's a z-value instead of a t-value. So if we have a proportion from 105, p is equal to 0.73, and we want a 95% confidence interval. The standard error of, or the standard deviation of the proportion, standard deviation of the proportion is 0.73 times 0.27, which is 0.44. The standard error of the proportion is just like the standard error of the mean. S over the square root of n, 0.44. So now if I want a 95% confidence interval, I need the norm.s .inv 0.025 or norm.s.inv 0.975. And this comes up to be 1.96 on the high end and minus 1.96 on the low end. So it's 0.73 plus and minus 1.96 times 0.043 0.73 plus and minus 0.08. And for this, 0.08 is called the margin of error. Add and subtract 0.65, 0.81, so that the real proportion is somewhere between 0.65 and 0.81 with 95% odds. It's no different than the bet on the mean, on the average, except that it uses the z-value, not a t-value. So there's no degrees of freedom with it. So that's a proportion, exactly the same. If you look in My Open Math, in confidence intervals, estimates in confidence intervals, confidence interval for the mean. It's confidence intervals including average. And we'll start with the page that says mean. This is 100 samples of size 30. And the bet is in anything that the real mean is between the lower limit and the upper limit with certain odds. This is, the blue dots are the upper limits and the yellow dots are the lower limits for a particular sample of size 30. And there's 100 of them. And up in this spot is the level of the probability. So this is 0.1. This is an 80% confidence interval done 100 times with a sample of size 30. And this shows here how many of those include the mean. The bet is 80% confidence interval. In this particular iteration, 83% of those confidence intervals contain the mean. These are real bets. This means that 20% of the time, the confidence interval will not contain the mean. And that's what the graph shows. The blue line across the center is the actual average. Any confidence interval that has a blue mark above that line does not include the average. Any confidence interval that has a yellow mark below the line does not include the true mean. If you say, I want an 80% confidence interval, you're going to miss about 20% of the time. And if it's enabled and you do Shift F9, it will run another iteration. Or just change something and it will do another one. So this one, I got an 80% bet that I asked for, and I got 87% hits and 13% misses. I'm going to pick a spot and put in something, hit enter, and I get a new set of iterations. So now my 80% says it's going to do 86. And if you keep doing that, it will eventually show more, show less. On the average, it'll be an 80% bet, but in this particular iteration, 75% hit and 25% didn't. If I change it to 0.025, 95% bet. Here I have 94 out of 100 hit. The other 6% missed. 96 out of 100. 98 out of 100. 95. 94. This is what happens. We make bets, we miss. The insurance company making bets on car insurance is using a much larger sample size. But even at that, they're still going to miss, so that you're not guaranteed on the sample. It simply works out exactly the way the probability says. So now we've got another problem, which is, does the situation change? This is house insurance in the fire areas in California. Houses burned down, and they didn't have the insurance set up to cover that. It was covering a different situation. So that I've got statistics that miss, but if I'm betting on the wrong thing, then I'm going to lose again, or I'm going to win again. So that the insurance company figures out exactly what they need, and then they hedge that bet by quite a bit. If you look at, at the proportion, this is the next page. It does the same thing. We've got the same probability set up. This is set up to do 95, and for this one, 96% hit, 4% didn't. If I change this to an 80% bet, 0.1. Here, 74% hit, 26% didn't. Purely because that's the way it came out, on a random basis, out of 100 possible samples of size 30. If I increase the sample size, I get the same percentage result. All the bets are just narrower than they would be otherwise. Sample size affects the accuracy by making the intervals narrower, but it does not change the probability that I got it right. So if I have a 80% bet, it's an 80% bet, no matter the sample size. 20% of the time I'm going to get it on the average. got that backwards. 80% of the time I'm going to get it, and 20% of the time I'm going to miss, regardless of the sample size. This is not the way confidence intervals are normally done. There is a percent interval rather than a value interval. So instead of saying I want to be within plus or minus 3 feet or something like that, it's I want to be within plus or minus some percent of the mean. And this has a way, affects the way you can assess the bet. You familiar with Canadian gas mileage? We do gas mileage in miles per gallon. The Canadians do it in liters per 100 kilometers. And it's just the opposite of the miles per gallon. It's 1 over miles per gallon with different units. So that if I have miles per gallon and I have liters per 100 kilometers. If I take the American miles per gallon, the Canadians have an average of 7. Put it over here. The Canadians have an average of 7 liters per 100 kilometers. And on the miles per gallon, we have 25 miles per gallon. And I'm just making this up. The standard deviation is 6 miles per gallon, and the standard deviation here is 2 liters per kilometer. I want to compare these things so that if I use a sample size of 100 for both of these things, the standard error here is 6 over the square root of 100, which is 0.6. Here, it's 2 divided by the square root of 100, which is equal to 0.2. So I have, on a 95% bet, 25 plus and minus 2 times 0.6. And always multiply the probability level by the standard error, then add and subtract. This is 7 plus and minus 2 times 0.2. So I get 25 plus and minus 1.2. This is 7 plus and minus 0.4. This part is the margin of error. Instead of saying 25 plus or minus 1.2 or 7 plus or minus 0.4, I want to know if there's a difference in this bet. And I can remove the units if I make the confidence interval a percent of the mean. In both cases, even though the units are completely different, if I take 1.2 and divide it by 25, I get 0.048. So that for the American cars, or the American specification, I have 4.8%, plus and minus 4.8% of the mean. For the Canadian miles per gallon, or liters per kilometer, it's 0.4 divided by 7, which is 5.7%. So is there a difference, really, between the cars? The cars are made in the same places. They just put a different label on it. But instead of doing liters per kilometer, liters per 100 kilometers, and miles per gallon, I make it a percent of the mean. So that these things are usually expressed as a percent of the mean. I don't need to know what the mean is. Here it's 25 plus or minus 1.2. Instead of trying to get an add, subtract, and getting a value in miles per gallon, I get it as a percent of the mean. And most people, when they're asking for a specification for a confidence interval, will tell you they want 95% odds on a plus and minus 10% bet. So they want to be within 10% of the mean with 95% odds. Forms are for. We've got fish. Average is 65 centimeters. And there are 100 fish in the sample. The standard deviation is equal to 40. And it's in centimeters as well. The standard error of the mean is 40 divided by the square root of 100, which is equal to 4. 4 over 100. 4 centimeters. I'm going to make a series of bets using different values for the confidence interval. Look on this sheet with the percent confidence intervals. On the left side is what the interval is. There's a 99, a 95, 80, 68, and 50. And on the right-hand side is the z value, basically, or the t value that gives me that confidence interval. So if I want a 50% bet on this length, 50% bet, it's 65 plus and minus 0.7 times 4. So I've got 65 centimeters plus and minus 2.8 centimeters. This is 62.2 to 67.5. That's in centimeters. The 68% bet is 65 plus and minus 1 standard error. This is pure empirical rule. 68% bet is 1 down, 1 up. 95% bet is 2 down, 2 up, times 4. This is 61 to 69. 80% bet. 65 plus and minus 1.3. 65 plus and minus 5.2. My bet is 59.8 to 70.2. There's a 90% in there. 90% bet. 65 plus and minus 1.6 times 4. Which as an interval is 58.6 to 71.4. The only thing that changes in all of these bets are the odds. The average doesn't change. The standard error doesn't change. All I'm doing is changing the odds that I got the right answer. So basically, all of these things are the same. and it's just looked at from a different angle. 95% bet, 65 plus and minus 2 times 4, 2 up, 2 down, is 57 to 73. If I graph these things on this other sheet that we've got, it's got the 25 minus 20 to 20 and a blank on the top. Use the part on the top. We want the blank one. And we're going to graph these intervals. So I've got a line here, and it's already written on yours. Here's the middle at 65. So go to the middle of the line, that base, and put in a 65, and then add and subtract 1 going each way. 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 64, 63, 62, 61, 60, 59, 58, 57, 56, 55. So my 95% bet, and there's a 99% bet on there. If somebody wants a 99% bet, they are asking for virtual assurity. And the interval is going to be immense. So wide that it is useless. But they will be certainly right. It's like, here I've got 65 as the average. If I want to know exactly an interval that covers the possible range of averages, I would go from minus 65 to plus 150. I've got it for sure. And it's completely useless. So the more sure you want to be, the less usefulness the interval is. So this one, 57 to 73. Find the 57 and the 73. 71, 2, 3. And there's my 95% interval. Mark the next one. The 90% is 58.6, somewhere here, 71.4. That's the 90%. The next one is the 80%, 59.8 to 70.2. These are always symmetric. The 68% is 61 to 69. That's the 68. This is the 80. And the 50, which I don't have room for on here, 62.2 to 67.5. Those are the actual confidence intervals. Now, I can use this to make bets. Confidence intervals are symmetric, decisions aren't symmetric. So depending on what part I want to cover against, I can cut this off at different places. Here I've got the 68% bet, and on this side is 16%. I don't have to use any particular one of these. I can use them in combination. So that if I want the chance that it's between the upper end of the 95 and the lower end of the 68, I can get that probability. So here is 95. This is 68. I got a 16 down here and a 2.5 there. So basically, I've got 100 minus 18 1/2. I've got a different interval, I've got a different bet. It depends on what side I want to cover myself on. All of these things have two ways to look at them. An easier way to do this now, instead of doing this here, 0.7 times 4 and so on, I can do this as a percent of the average. I've got the margin of error divided by the average. So for a 68% bet, this is plus and minus 4, one standard error up and down, divided by 65, which is equal to plus and minus 6%. What is the 95% bet? 1 up, 1 down for 68, 2 up, 2 down for 95. That makes this a plus or minus 12% bet. Then go back here to this one. At the bottom, it shows the percent margin of error. Find 12 on that scale. Five, 10, 15, 20. I want 12 on the scale. Then up at the top, there's a 95% line. Go up from 12 until you hit the 95% line. Then draw a line from 0 through that point. All the possible intervals are on that line. So if you look at the 6%, plus or minus 6%, look where plus and minus 6 hits one of the confidence interval lines. And it's going to be at the 68% bet. The plus and minus 4%, where is the 4? Where does it cross one of the percent lines? Got my lines out of scale. Got it in the wrong place. All of these things, once I've drawn that line in there, all I have to do is go to the others. There's the 90% bet. Follow that till it hits the line and go down, and what are you at as a percent? Which is what I get from the calculation. So that doing these as a percentage simplifies finding out what the bets are. So that instead of this here, I can make another stack, 0 plus and minus 12%. 5, 5, minus 5, minus 10, minus 15, 10, 15, 12 is the 95% bet. At basically 10, 9.5 is the 95% bet, plus and minus 9.5. Plus or minus 8 is the 80% bet. Plus or minus 6 is the 68% bet. And plus or minus 4 is the 50% bet. So that instead of having to do this in real numbers, I can do it as a percentage much more quickly and decide what part of this bet do I want. So all of these bets are the same thing. Draw a line over the top of those curves, those boxes. What do you get? It's a normal distribution. This is a consequence of the way all of these things come out, what they come from. So that doing a confidence interval as a percent of the mean simplifies things, brings it all down to one graph. And if you remember, 2 up, 2 down is 95. 1 up, 1 down is 68. You can get all the rest of them by drawing a straight line. All you need is any one of them. Also, if you look at your graph, where's the 99% bet? On your graph, where does this line cross the 99% line? Yeah, I haven't got it on here. But it's basically, it's this wide. And look at the way the stack is spread out. Here, this difference is 18 from 50 to 68. This one goes 22. This is 5. That's 4. They aren't even up there. They're even only in terms of the t values that bring them about. So that 99 is like this, 95 is in further, but then as you get closer and closer to the middle, you start to get the half-inflated basketball, where you can't push it in any further. So that's percent intervals, proportions for intervals, and you can do the proportions in the same way. The proportions actually are already in percents. You've got 40% plus or minus 3%. It's the same graph. So that puts the proportions and the averages on the same basis, all as a percent of the mean. So when you see something, figure it out as a percent of the mean. And then you can convert it to other things that might be more important. Confidence intervals as a percent of the mean is the way to go. It's much easier to interpret. It's easier to explain. And the explaining part is where things get exciting. Explaining the statistics is much more important than actually being able to do the statistics.